Welcome everyone to this last video, specifically on limits, and more particularly in this case on indeterminate forms of limits that involve infinity. In previous sections we encountered 0 over 0 forms and discussed how they must be treated as indeterminate. Rather than calling them undefined, you have to recall that 0 over 0 meant that more work needed to be conducted in order to establish whether the limit exists or not. The same can be said of forms that involve infinity. In this section, we're going to discuss indeterminate forms as well as techniques to handle them. The form we will encounter the most often is the infinity over infinity form, but it will be caused by different types of situations. Infinity over infinity forms will most frequently occur in situations that involve rational, radical, or exponential functions. In all three of these cases, the most efficient strategy will be to factor the most important term, that is the one whose size is becoming the greatest, from the numerator and from the denominator respectively. It's after simplifications that we'll figure out if we have managed to remove the indeterminate form. So for scenario, infinity over infinity forms involving rational functions. So by rational functions, recall that we are referring to a ratio, a quotient of two polynomials. So in this example, we have two polynomials of third degree, with x heading towards infinity. We've shown in the previous video that polynomials always have extreme behaviors at the extremities. So in this case, we are encountering an infinity over infinity form because 4x cubed and 2x cubed, the two main terms of the numerator and denominator, are becoming infinite as x goes to infinity. So the strategy we'll use will be to factor the most important term, so the ones with the greatest size, from the numerator and denominator respectively. So at the numerator, x cubed is the term of highest degree, and x cubed is the term of highest degree at the denominator as well. They are also the terms that are the biggest in size as x grows towards infinity. The fact we have common x cubes allow us to cancel those terms. And then we can re-evaluate the new limit with the simplified expression. Remember that all numbers, all constants divided by infinite size terms will go to 0. So 2 over x squared, 4 over x cubed, 1 over x, and 5 over x cubed actually become 0 or tend towards 0. Which leaves 4 over 2. We're going to factor the most important term from the numerator and denominator respectively. This strategy is also applicable in the situation where we are heading towards minus infinity. So this is the same rational expression that we had earlier, but now we're going to head in the other direction. X cubed is still the term whose size is biggest when we head towards the extreme left-hand side. And that's also true at the denominator. Once again, the biggest terms can be eliminated. So I've eliminated the common x to the power 3's from top and bottom. And the outcome of this limit will also be 2 because all terms, 2 over x squared, 4 over x cubed, 1 over x, and 5 over x cubed tend towards 0 when divided by an extremely big number. So, conclusion, y equals 2, the answer to both limits we have just conducted, is a horizontal asymptote of the rational function at both extremities. And here is what this function looks like graphically. Now you can observe that at both edges, the function is reaching for or heading towards a height of 2. Infinity over infinity forms that involve roots are a little bit more subtle. So as an example, we're going to use the limit as x goes to infinity of 4x plus 3 over the root of x squared plus x plus 2. So it's a quotient, but it involves a square root in this case at the bottom. Direct substitution will indicate that an indeterminate form is obtained at first because we clearly have an infinite size trend at the top as well as at the bottom. As we did before, the strategy we'll apply will be to factor the most important term, so those of biggest size, from the denominator and the numerator respectively. At the top, it's actually quite straightforward. X is the biggest power we see, or x has the biggest power we see. We can factor it to leave 4 plus 3 over x. At the denominator, x squared is the biggest term that we encounter within the roots. So as a first step, I factored x squared. That x squared term is still in the root though. So it's hard to cancel off any terms for the time being. But if we extract x squared from the root, we will actually be able to make some simplifications. And now here's where we have to be really careful. The root of x squared is not always equal to x. Remember that a square root always produces a positive outcome. So the root of x squared is equal to the absolute value of x, and not necessarily x. Now the good news is, in this case, x is heading towards infinity. And because x is heading towards infinity, this choice of making root of x equal absolute value of x may not be as influential. The fact that x is going to plus infinity means that we already know x is positive. The absolute values will not have to do anything. We can cancel off the x's, and most of the terms that remain tend towards 0, aside from the 4 at the top and the 1 in the root. So 4 over root of 1 is 4. Now, the other extremity also requires that we pay some attention. Same process, x is the biggest term from the numerator. X squared is the biggest term within the root, and I factored the x and the x squared. At the numerator, factoring has already been done, where the biggest term has been extracted. At the denominator, I have once again replaced the root of x squared by the absolute value of x. I'm always keeping in mind that rooting a number must have a positive outcome. And this time, because x is heading towards minus infinity, it's actually the root minus x, or the absolute value of x is equal to minus x. That is a positive outcome. Think of x as a negative number. Well, minus x would then become positive. Simplifications will leave a minus 1 outside, and all the terms that have an x divisor will go to 0. So minus 4 will be the outcome this time. Conclusion, the function that we have been working on the last two examples has y equals 4 as a horizontal asymptote at the right extremity, but y equals minus 4 at the other. And here is its graph. Finally, we have infinity over infinity forms that involve exponential functions. So for example, let's look at what will happen to e to the 2x minus e to the minus x over e to the 3x plus 3e to the minus x as x goes towards infinity. Very important is to remember what the effect of x going to infinity is on all terms. E to the 2x and e to the 3x will take on e to the infinity forms when we do direct substitution, and those are infinite. However, e to the minus infinity is what we get from direct substitution on the two other terms. They tend towards 0. So who are the influential terms? Well, at the top it's e to the 2x, and at the bottom it's e to the 3x. This is an infinity over infinity form, but it is caused by the first terms of the numerator and denominator specifically. So factoring out the most important terms in this case would mean factoring out e to the 2x from the top, e to the 3x from the bottom. By using properties of exponents, remember that common base exponential functions, the exponents would add, allows us to figure that by factoring e to the 2x, we'll have 1 minus e to the minus 3x at the top. And by factoring e to the 3x, we'll have 1 plus 3 e to the minus 4x at the bottom. If you're not sure of this algebraic manipulation, redistribute to verify. E to the 2x and e to the 3x have some terms in common. In fact, because we're dividing, we can subtract the exponents, and there is an extra x at the bottom exponent compared to the top. So e to the 2x over e to the 3x leaves e to the x at the bottom. And now we're ready to try direct substitution again. At the top, e to the minus infinity becomes 0. So e to the minus 3x and e to the minus 4x, for that matter, both tend towards 0 because they are e to the minus infinity forms. It leaves 1 at the numerator, and it leaves e to the infinity times 1 at the bottom. E to the infinity tends towards infinity. So 1 over infinity goes to 0. Once again, just to contrast, here is the same expression, but where we are looking at the limit as x goes to minus infinity. Direct substitution, this time, reveals that e to the 2x, as x goes to minus infinity, and e to the 3x create e to the minus infinity forms. They go to 0. E to the minus x, with an x value going towards minus infinity, and 3e to the minus x, with x going towards minus infinity, generate e to the infinity forms. So this time, we do get an infinite over infinite size ratio, but caused by the last terms of the numerator and denominator. Remember our strategy. Our strategy is not to factor out the biggest exponent, it's to factor out the terms of greatest size. And in this case, the terms of greatest size are the e to the minus x that appear top and bottom. So that's what we'll factor. And using properties of exponents, we can determine that we are leaving e to the 3x minus 1 behind from the numerator, e to the 4x plus 3 behind from the denominator. Again, redistribute e to the minus x to both the top and the bottom if you want to validate that this was done correctly. E to the minus x are now common to the top and bottom and can be eliminated. And we're ready to do direct substitution again. E to the minus x is what e to the minus infinity, is the form that e to the 3x and e to the 4x will take on as we do direct substitution. Remember that e to the minus infinity goes to 0. So minus 1 and 3 are the lone constants that remain after direct substitution. As a conclusion, this time we found that 0, y equals 0, is a horizontal asymptote of our function at the right extremity, and we have found a very different horizontal asymptote at the left, which was minus a third. Again, here's a graphical verification of what our numerical work has concluded.